All right. So guys, sorry for the sort of slow start, but before we dig into looking at homework answers, I just need to tell you, there's the possibility I won't be here on Tuesday. Right now, one of my very best friends on the planet, his mom is in the process of leaving us. And frankly, it's amazing she's still alive. She's a very strong woman, but she's on her way out, which is actually a good thing. It's time. But guys, if things go as I would be surprised if she's still alive right now. But anyway, if that's the case, then the funeral will be on Tuesday, and I won't be here. So you're going to want to be here. I had sort of a moment of clarity yesterday while raking up my 12th and 13th bag of leaves. And we're going to do something on Tuesday, assuming that you're with a sub that you're going to want to be here for. So plan on Tuesday. If I'm here, we'll see. We may do it anyway, not sure, but we'll see. So, guys, with that said, I will also not be here today for Flex and after school. Truth be told, I'm going pheasant hunting, so see ya. So, guys, with that said, questions about the homework?
On question 45,
yeah.
B and C.
Yeah.
How are you supposed to tell whether it's ionic?
Okay, so let's talk generalizations, then let's talk realities, then let's talk crazy. Okay, so guys, the question on the table is, how do you know if something is ionic or covalent? And again, guys, we've got generalizations, reality, and then crazy. So let's do generalizations first. So when we started last time, or maybe, no, 2 times ago, we talked about the idea that we've got metals and they're big and fat and weak, and then we've got non-metals and they are small and strong. So in general, what we're going to say is this: metal to non-metal, ionic, non-metal to non-metal, covalent, and then metal to metal, metallic, of course. But we're going to say these guys form covalent bonds, these guys and these guys form ionic bonds. Is that okay? So that's really where we're going to leave it relative to the test. So now let's talk about the real answer. So guys, if you have your periodic tables, the good ones, if you will, if you grab those, there's a better answer to Ethan's question. Turn on the back. And even if you've got one to share with somebody next to you, that would be great. But again, guys, the question on the table is, how do we know if something's ionic or covalent? Guys, remember that ionic and covalent comes down to electronegativity, right? If you follow the idea, the reason that a metal and a non-metal form an ionic bond is because the non-metal has a high electronegativity, the metal has a low electronegativity, and that results in stealing. And then, guys, 2 non-metals, when they get together, they both have high electronegativities, therefore neither one wins and they share. Which then begs kind of an obvious question. How different do they have to be for ionic to take place? Right? Guys, do you see the chart up here at the top? If you look at it closely, you'll notice that it says percent ionic character of a single chemical bond. And at the top, it's got difference in electronegativity, and then at the bottom, it's got percent ionic character. So the higher the ionic character, the larger the difference in electronegativity. And then, guys, smaller electronegativity differences means they're more equal in strength. As a result, the character of the bond is less ionic, and therefore we think of it as covalent. Please don't do that. You get the idea? So where's the cutoff? Where's the 50%? Yeah, it's actually 1.67. So guys, we call the turning point between the two 1.67, which is not a number that you need to know. But this is where things get weird. Guys, what if the difference in electronegativity is 1.66? Does that mean it's covalent? And what if it's 1.68? Does that mean it's ionic? And Ethan, this is where things get weird, because there's no such thing as a purely ionic bond. If you look, the greatest difference in electronegativity, which is clear off on the right-hand side, is still not 100% ionic. There are examples of pure covalent bonds. You want to guess where they are? Yeah, the diatomics, carbon to carbon, hydrogen to hydrogen, those are understood to be purely covalent, especially nitrogen to nitrogen, because it's a triple bond and it's really symmetrical. But understand, there's no such thing as a purely ionic bond. Even if we've got huge electronegativity differences, we still have a little bit of sharing taking place. So it's really a continuum, and the middle is 1.67. Is that okay? Now let's talk about the weird. There are some substances where we don't know if they're ionic or covalent. We literally can't tell if it's a salt or a molecule, and they're not that exotic. A lot of the permanganate-containing compounds, we can't tell if they're ionic or covalent because they kind of behave like both. And so it's definitely not clear-cut. So what we're going to do is we're going to say metal to nonmetal is ionic, and then two nonmetals is covalent. That was a big answer to a short question. So then coming back to this, that's where my answers came from, sort of, because if you look, for example, here we've got two different metals bonded to chlorine. This is where we need to start talking about that 1.67 deal. But also, and so they wouldn't expect you to know this on the test, but maybe something to think about. Maybe something to think about in this case is that if you look at the way they're named, this is the naming convention for a salt, Roman numerals. This is the naming convention for a molecule with the prefixes like hexa. Those are clues as well that can help you figure out which one they are. Guys, other questions on the homework? You guys okay? Please, Maddie, just a second, Josh, go ahead, Maddie. Hold on. 50, yes. Yeah, oh yeah. Say that again. Oh, yeah. Okay, so guys, I'm so glad you caught that. That's awesome. So guys, looking at 51C, you should have been able to draw the Lewis dot structure for 51C just by tracking electrons. Oxygen's got 6, bromine's got 7. But you ran into a problem. And guys, you ran into a problem because bromine has to be in the middle, but it's a halogen and can only form one bond, right? No. So, guys, here's the deal, and we're going to talk about this a little bit at the end of the day today. Last year, in general chemistry, where I protected you from all of the weirdness, you learned that halogens can only form one bond because they have 7 valence electrons. Well, guys, it turns out that the halogens actually can form not just one bond, but 2 and 3 and 4 and 5 and 6. So guys, it turns out that the halogens actually not only can form more than one bond, they can actually even form molecules where they have more than an octet. And guys, this is where this gets really interesting in Chapter 9 when we start talking about molecules that have more than a full octet. And how does that happen? We'll talk next week when we get into Chapter 9. But Maddie, right now, yes, given what you thought you understood, bromine can only form one bond and that shouldn't work, but it turns out that it can. But even at that, even if you were like stuck and you're like, wait, I can't draw the Lewis dot structure, once you copy down the Lewis dot structure, you should have been able to figure out the formal charges.
Yeah, the formal charges, and it even tells you in the textbook with that specific problem, it says the oxygens are all formed around the central.
Oh, nice. Okay.
So it, like, I was confused until you did that.
Yeah, that's awesome.
Next one was chlorine.
Yeah.
Bonding sites.
Yeah, right. And so, and it's actually, I didn't know that they did that. So Eugene or whoever wrote the question knew that you hadn't been into chapter 9 yet, so they gave you the clue that this is what happens. That's awesome. We'll talk more in chapter 9. Josh, you had a thought?
Yeah, I have a question.
Yeah.
Can you go over how you count the charges again? Can you do it last time I told you?
Do you want to do, like, could we just do letter A just because it's most convenient? Is that what you mean?
Yeah, but that one's all zero. That one's kind of easy. But like I'm talking about like finding the formal charge. Maybe do C, which is kind of like difficult.
Okay, so remind me. So it looks like we're finding.
And oxidation.
So we're finding oxidation numbers and formal charges. And do you want to do both?
That would be great.
Yeah, let's do both. That's fine. Sure. Okay, so. Let's do formal charges first. So formal charges, remember the concept, it's about cold dating biker chicks, right? It's how much change. And so when we measure change, it's a before and after picture. So the before picture is valence electrons. Oxygen has 6 and bromine has 7. Right? Then, to figure out the after picture, we count electrons where bonds count as 1. So this oxygen's got 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is minus 1. This bromine's got 1, 2, 3, 4, 5. 7 minus 5 is 2. This oxygen's got 1, 2, 3, am I in your way? Can you... Okay, so 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is minus 1. And then 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is minus 1. Is that okay? Okay, now let's do this. So in order to figure out the oxidation numbers, is that the molecule? Is that right? Let's just call it BrO3, and then we're going to go minus 1. And so the idea is this, that to figure out oxidation numbers, we need a fixed point. And if you look at bromine, bromine's got like 1,000 different charges, well, 5 different charges it can have. If you look at oxygen, oxygen is minus 2. So if oxygen is minus 2, and there's 3 of them, this is minus 6. So if this is minus 6, what does bromine have to be to make the whole molecule minus 1? And that's plus 5, and that's those.
Oh, so I'm so confused.
Yeah, so remember, we did oxidation numbers really briefly back in the very first unit when we were talking about redox reactions. And so we said that the way to find out oxidation numbers is to find a fixed point, which is usually the second one, in this case oxygen. And then the oxidation numbers have to add up to the charge of the ion if it's an ion. And so if this is minus 2, minus 6 plus, is that,
Yes.
It's a little review.
Just the charges on the like in the molecules, essentially what charges.
Exactly, yeah, it's the charge. Well, but you have to be careful because this isn't ionic. So when we talk about and this is where your college professors are going to do this better because we've got ionic charges. So like, for example, in NaCl, sodium's plus 1, chlorine's minus 1. Then in a molecule, we have oxidation numbers. And what we've said in this class is they're the same. The oxidation number and their charges are the same. Technically, that's not true. That if we say that this is 1 plus and 1 minus, that's the number of electrons they've lost or gained. So charges are ionic bonds. When we talk about oxidation numbers, this doesn't tell you how many they've lost or gained, it's telling you how many they share. And so oxidation numbers apply to molecules because they're not ionic, they're sharing covalently. In this class, we've said that they're the same, and that works. So if you know the oxidation number, you call it the charge, it doesn't matter. But and that's true on the AP test as well. But in college, they'll start to tease these apart for you. For now, they're close enough. Yeah. Great questions. Guys, anything else? You all good? Oh, yeah.
Which elements are we supposed to know their like how many bonds they have? Like how are you supposed to
Yeah, and that's interesting, right? So we can always, so guys, if you didn't hear Kaylee's question, she's like, which ones do we need to know the number of bonding sites for? And the answer is you can always predict generally, and it's actually easier to work backwards. So this has got 8 valence electrons, so that would be none. This has got 7, so that would be 1. These have got 6, so that would be 2. These have got 5, so that would be 3. These have got 4, so that would be 4, and so on. And that's all we need to do, because remember, it's only the nonmetals that form covalent bonds. So the general trend goes backwards from 8. But then, and that'll get you through chapter 8. Obviously, it's not going to get you through chapter 9 because of things like this. And actually, sulfur's broken too. Because if you look at sulfur's like oxygen. It should only have 2 bonding sites, but it forms 3 bonds. How does that work? You're going to find out in the next unit. The way that it works is d electrons become valence and form bonds. We used to think that the valence shell was only the s and the p. Actually, d electrons can become valence and form bonds, and that's what's going on there and in bromine. But the bottom line is you technically don't need to know how many bonding sites they've got. You just need to be able to draw Lewis dot structures and make everybody have an octet. Is that okay? Were you going to add something to that? Exactly, yeah. But this is the thing that's really, I don't know if you heard what Eleanor said. She said, is that how sulfate and sulfite work? And the answer is yeah. So if you look at something like sulfate, which is -2, it's this, right? And you're like, wait a second, how does sulfur form 4 bonds if it's only got 2 bonding sites? And we just talked a little bit about the idea that the d electrons can get involved. The other thing that can happen is electrons can come in from the outside that allow the central atom to have more than an octet. And that's what's going on, or form more bonds than they should. And so let's talk about it really quickly. So how does sulfate work? And the answer is really interesting. If you draw the Lewis dot structure for sulfur, it looks like this. And so what happens is an oxygen comes over here, and I'm going to draw oxygen's electrons as X's, just to keep track of them differently. And then another oxygen comes in here, and I'm going to draw its electrons as X's as well. And this is where this gets weird. Another oxygen comes in here, and it actually forms a covalent bond, but the 2 electrons that form the bond both come from the sulfur. And then another oxygen comes in here, and it does the same thing, forming a covalent bond where oxygen is not donating an electron to the bond. But then you'll notice that this leaves 2 holes, right? We've got a hole here, and we've got a hole here, and that is where the charge of this becomes critical, because then 1 electron donates into this hole, and 1 electron from the outside donates into that hole, and that stabilizes the molecule. If these electrons were not available, this molecule would fall apart. And we'll talk more about that in chapter 9. Yeah, it's an interesting thought, though. I know, it's interesting. You guys, other questions? Josh, did we do yours okay?
Yeah, I was just with that, when you were talking about answering your question, I was just thinking, like, so is it, I mean, I don't care if it says, but is it like better to maybe like disregard the bonding site?
Absolutely. And that was my point. Now you have context for what I was trying to say the last time in class. I'm like, guys, you're going to get into college and your professors are going to teach you all these ways to draw Lewis dot structures where you have to do the accounting. Oxygen's got 6, it's got 2 bonding sites, and try to do all this. The way that I taught you to do it, you can disregard bonding sites, just huck everything together and start filling octets. And so that's exactly why I said to Kaylee, don't worry about bonding sites. It's because of that. Yeah.
So just do it by chart.
Exactly, precisely. Anything else? So guys, let me mention one other thought. So why did they have you come up with formal charges and then come up with oxidation numbers? And guys, there's actually some really interesting things going on there that we don't need to talk about. So you're not, probably in college you'll have professors, especially if they have a background in organic chemistry, or if they're organometallic chemists, they'll be talking with you about the relationships between oxidation numbers and formal charges. We don't need to do it, but that was, anyway, a precursor to it. So, are we all done with this? Are we good? Okay. So, guys, let me get your homework performances recorded. You do need your books open. I'll give you page numbers in a minute. Let me pause. I did again. Okay, so guys, covalent bonding, part 2. So guys, today goes fast. You will get a lot of your homework done today, I think. This is quick. But my screen is frozen. Starting again, covalent bonding part 2. So, guys, in order for us to have an intelligent conversation about what we're going to talk about today, and we're just digging deeper into Lewis dot molecular structures and molecules, guys, in order to talk intelligently about what we need to do today, we've got to establish some ground rules that you're going to see are painfully obvious. But we still have to talk about them. So guys, what we're talking about is what is called bond enthalpy. Definitely a term worth scratching down. Even though it is painfully obvious, it's worth talking about at least the definition. So guys, first of all, this. Bond is now self-explanatory, but what do we think of when we think about enthalpy? Heat, energy, endo and exothermic. Guys, which is which? Is exo negative or positive? Negative. Positive is endo. So guys, what we're talking about is heats or energies related to bonding. And guys, we went over most of this stuff when we did Hess's law. Remember the idea that if you can add up the bonds have to break and then bonds have to form in order to reactions to happen? So guys, technically then the definition is simply this. Bond enthalpy is the amount of energy that's needed to break a mole of gaseous molecules into their component atoms. That is the definition. But guys, it's important that you understand why it's important that this is a gas. Actually, here, I want to do this instead. Okay, so guys, here we have a water molecule. So when we talk about bond enthalpy, looking at my water molecule, bond enthalpy is the amount of energy to do what? Break this and that, right? So guys, literally it's the amount of energy needed to break this into its component elements. Now guys, here's the important question. Why does the water have to be a gas and not a solid or a liquid? Oh, you're a genius. Guys, if you were talking about a liquid or a solid, we'd also have to break the IMFs. And that would, if we were doing this in lab, that would give us an improper value because a lot of the some of the energy that we're putting in is breaking the intermolecular forces and not the bonds. So these things have got to start in their gas phase, so the only thing that we're breaking are the bonds and not the IMFs. Well done. Are we good? Okay. So guys, what about this? These values are always positive. Remember how we talked about endo and exothermic a second ago? Guys, why? Why is that true? Why are these values always positive? Always. But what is the important principle that is based on? But what's the important principle? Guys, in order to break something, what do you have to do? Add. It doesn't matter if it's a rock or a bond. Guys, if you want to break something, you've got to add energy to it. Always. This is one of the few alwayses in this class. You got to add energy to get something to break. And so, guys, these values are always positive because energy always has to go in order to break the bond. You guys all settled on that? Okay, these then are some interesting things that are very commonsensical, but you should at least be exposed to them, even though most of you are going to look at these and go, duh. So, guys, first of all, stability. The greater the bond enthalpy, the stronger the bond. Duh. Guys, the more energy that it takes to break something, the stronger that something is. Huh? There's a name for that. It's called obvious. It says, see, I'm glad that you caught that. And then, guys, you don't need to write this down, but so these are, well, that, if you don't, greater stability. And then, guys, please don't write this next bullet down, but we talked about the idea that we can add these up for Hess's law. We brought those ideas together, but just giving you context, we already talked about it. But, guys, this is what you need to know. Bond enthalpy is the amount of energy to break a bond. The bonds, maybe in a molecule, it's always endothermic. Energy always goes in. The more energy that's required, the more stable the bond. Good? Okay, now we need to do this, and I think this is also going to be kind of a duh, but let's talk. Guys, we need to, I'm going to just get rid of that. I don't like this. It's sort of like just out of nowhere, and we already talked about the connections, so let's just make that go away. Guys, we need to now relate this to bond length. Not all covalent bonds have the same length. So guys, which bonds do you think are going to be shorter, the strong ones or the weak ones? Strong ones. So guys, the stronger a covalent bond is, the shorter it is. That's true in ionic bonds too, right? The bigger the ions get, the weaker the bonds get because the space between them increases. So guys, the closer together things are, the more tightly bound they are. Oh, we could even come up with some touching marriage analogies for that too. How could we include Cole and his biker friend? I was thinking about Cole cutting his hair so that she could get closer, but that doesn't work. Let's just not go there. All right. So guys, it's simply this. It's an inverse relationship. So the longer the bond, the weaker the bond, the shorter the bond, the stronger the bond. So as bond enthalpy increases, stronger bonds, the bond length decreases. And then this, guys, gets us to thinking about multiple bonds. That when we look at multiple bonds, double and triple bonds, the more bonding we have, double and triple bonds, the stronger the bonds will be. Doesn't that make sense? That a double bond would be stronger than a single bond. A triple bond is stronger than a double bond. So guys, if that's true, and it is, which is going to be a longer bond, a single bond or a triple bond? Which is longer, single or triple? Single. Single bonds are weaker, they're longer. Triple bonds are stronger, they're shorter. So guys, the smaller, as you get double and triple bonds, they're stronger bonds, and they have shorter, smaller bond lengths. Do you guys know this? What is the shortest, strongest bond that we know of? Do you guys know? It's actually the triple bond in nitrogen. nitrogen is diatomic and it triple bonds to another nitrogen. It's actually the shortest, strongest bond that we're aware of. It's kind of cool. All right. You guys all caught up? Can we all use this as a way of thinking about molecules and bonding? So bond enthalpy, breaking bonds, the stronger the bond, the shorter the bonds, double bonds, triple bonds get shorter as they get stronger. You good? Okay. All right. So guys, moving along then, what we need to do is, and actually we're going to back up into this a little bit more gently. Guys, what we need to do is we need to give ourselves a Lewis dot structure to think about. And so guys, what I'm going to ask you to do in your notes, and make it fairly big, like if you want to draw it maybe so big around. Guys, what we're going to do is we're going to take a look at this magic molecule, which is called ozone. You've probably heard of it. We have the Earth is surrounded in a blanket of ozone that does an amazing job of reflecting ultraviolet light from the sun. It's like sunscreen for the Earth, except for we have holes. You guys know about this? The hole in the ozone layer. Turns out it was because of chlorine. We'll look at the chemistry later. It's because of chlorine that we were dumping into our atmosphere as the propellants for like hairspray and refrigerants in our AC in our homes and our cars. And the chlorine was actually destroying the ozone molecules, and it put a hole in our ozone layer, and it was causing the Earth to heat up. And since then we fixed it. You can no longer use chlorine-containing compounds as propellants, and it's healed, but it looks like it's coming back, and we don't know why. Anyway, so guys, what is ozone? Draw its Lewis dot structure. If you want to get really crazy, you could even try to draw it three-dimensionally correct. Come on. Don't be scared. Did you get it? Let me try it. So we've got oxygen, oxygen, oxygen. So we've got what, 18 electrons minus 4. That gives us 16? Yeah. So maybe we go 1, 2, 3, 4, 5, 6, 7, 8. You guys have to understand I went to public school. So what you're telling me is 18 minus 4 is 14? Thank you. 2, 4, 6, 8, 10, 12, 14. And again, guys, it doesn't matter how you get these on the screen. You could have gone 6 and 4 and 4. It doesn't matter. In either case, we get to the point. It's just the oxygen. The way I drew it is just the oxygen in the middle that needs an octet. So we need to create a double bond. Did you guys approach it this way as well? So guys, when you get to the point that you have to create the double bond, do we create it to the left or do we create it to the right? It doesn't. But I like the way you said that. I chose the right, but it doesn't matter. And guys, if you don't understand why, let me build it for you really quickly. I think I've got some oxygens that are drilled with 3 holes. Maybe I don't. That's interesting. I thought I had some oxygens that were drilled with 3. I should. You know what, guys? Let me just draw it, and then we can talk about it. So I'm going to go, Josh, because you said right, I'm going to go left and do that. But there's an important reason for this, right? And guys, I don't know that I need to draw it. But now what's on Josh's paper, and probably what's on many of your papers, is the opposite of mine. But do you understand that really technically what we're doing is, in one sense, we're looking at it from this side. And then if you looked at Josh's, it's just like looking at it from behind. That if you had this molecule built in your hand, and guys, I'm disappointed that oh, there we go. Here. So if you build this molecule, it actually looks like this. Hey, thank goodness. So it looks like this, but the idea is that if you've got it the way I drew it, it's like this. But if you look at it Josh's way, you're just flipping it like this, right? So whether it's on the left or the right, it's the same molecule. Yeah? Okay. So, guys, now let me bring, well, actually, before I bring it in, I did this digitally too, and we'll talk about it. Guys, this is the question now you should be able to answer. I'm going to number these because we really can't say left or right. But, guys, bond number 1 or bond number 2, which one is shorter? Bond number 1, because which one's stronger? Also bond number 1, because we established on the previous slide that double bonds are stronger and shorter than single bonds. Is that okay? Okay. Guys, now let's get into what we actually are going to talk about today. So, we've established the idea that ozone has got a double bond and a single bond to oxygen, and that the double bond is shorter and stronger because it's a double bond. Good? Okay. Well, guys, here's the problem. It turns out that if we look at ozone, which I've drawn like this, it is actually bent. It turns out that this bond, we can measure its length. The length of this bond is you don't need to know this, but it's 1.278 angstroms. So guys, if that's true, what will the length of this bond be relative to this? Less. Turns out it's the same. And guys, this is where things get interesting. But it turns out that the length of these two bonds is exactly the same. But guys, it gets even more weird than that. Not only are the lengths of these bonds the same, but they are longer than a double bond and shorter than a single bond. Let's say it again. So, guys, again, not only are these two bonds the same length, but that length, 1.278 angstroms, is actually longer. Let me write this down so you can see it. Guys, that length, so oxygen can single bond and oxygen can double bond. This length, 1.278 angstroms, is actually longer than the length of a double bonded oxygen and shorter than the length of a single bonded oxygen. So guys, the question is this: what is going on? You guys ready for the answer? You're going to like this. Guys, this is what's going on. When we drew oxygen, when we drew ozone, we did this, right? And I said out loud, does it matter which direction we draw the bond? You all agreed no. Josh said he went right. I said that I went left. And then we talked about the idea that it doesn't matter if we went right or left, because those are the same molecules, whether it's right or whether it's left. You good with that? So guys, here's what's actually going on. That double bond does not form to the left, and that double bond does not form to the right. It forms in both directions partially simultaneously. Guys, this is what, and we're going to talk about this, but literally, guys, this bond forms in this direction, and this bond forms in this direction, partially simultaneously. Guys, this bond has a name. This bond is called Delocalized. This is what is called a delocalized pi bond. This is important. Put it in your notes. Guys, this is what is called a delocalized pi bond. A delocalized pi bond is a partial double bond that forms in multiple directions simultaneously. And guys, this happens a lot. So the question becomes, when does this happen? And the answer is, this happens when you have Lewis dot structures where you could create double bonds in one direction or a double bond in another direction, and those two directions are equivalent other than direction. So guys, if this was a bromine atom, that would not work. The two double bonds have got to be equivalent in terms of which is bonding to which. So we could have formed an oxygen double bond that way, or an oxygen double bond this way, and they are equivalent, and therefore it forms in both directions simultaneously. And guys, that is what explains the fact that these two bonds have the same length, because the double bond forms partially in both directions. And so guys, please don't ever say this out loud, but conceptually you can think of it as like a 1.5 bond. And the 1.5 bond is going to be shorter than a single bond, but longer than a full double bond. It's somewhere in between. Do you get the idea? But guys, you will never call this a 1.5 bond. You will call it a delocalized pi bond. And think about what it means. Delocalized means without location. It means that the bond forms this way and it forms that way simultaneously, and that's what delocalized means. You guys good on the ideas? So now, guys, here's the trick. Regardless of how you understand it, you've got to be very, very, very careful about how you talk about it. So let's look at that. Go ahead.
The question was, if this is a double bond and this is a single bond, but they're both the same length, they have the same strength.
They do. Yes. Yeah, but understand it's actually not a double and a single. Some people represent, this is not the way to do this on the AP test, but what you'll see is some of your university professors will actually have you represent it like this, where you'll write in partial, like dashed second bonds in both directions. So not only do they have the same length, they have the same strength, and they'll actually be a little bit stronger than a single bond, but a little bit weaker than a double bond. You guys good on the ideas? So how do we talk about it? And guys, this you want to write down. This is the way we represent this. In order to represent this, guys, we do not draw the partial bond in both directions. We draw both of these molecules, one with the double bond to the right and one with the double bond to the left, with a double-headed arrow between them. But guys, please be careful. Do not let this be your double-headed arrow. What does that double-headed arrow mean? That's equilibrium. And these are not at equilibrium. They are not switching back and forth. So guys, once you're done drawing these, we need to talk about that important idea. So I'll give you a second to draw these and then we'll talk. You okay? You caught up? Yeah, go ahead, Spencer. That's a great question. Can I couch that question for a moment? So guys, Spencer said, do each of these bonds only have one electron? And the answer is even more complicated than that. What I want to do is I want to drive home some ideas, and then we're going to look at another example, and then I can actually show you what the electrons are doing. Is that okay? Okay. So guys, let's make sure you're clear on this. If you put this on the test or the AP test, it's wrong. Here's why. This double-headed arrow means equilibrium. And guys, when you learned about equilibrium, you learned about the idea that reactants are becoming products and products are turning back into reactants, right? And if you apply that idea to this system, it's wrong, because this and this are not alternating back and forth. This double bond exists simultaneously in both directions. It's not flipping back and forth like an equilibrium system. So we use this double-headed arrow to represent the two different structures, but they're not flipping back and forth. They exist simultaneously, but only partially. Do you understand the difference? Okay, so these then, guys, are the things underlying this that you need to understand. So first of all, these two structures, they are completely equivalent other than the location of electrons. And Spencer, where are the electrons? And we're going to look. So guys, the actual then Lewis dot structure for ozone is the average of these two. It's not flipping back and forth. It is truly the average of these two structures. So guys, this then leads us to the term that we use for these. These are called conformations. So we represent this by including both of the conformations and a double-headed arrow that's not the equilibrium arrow. So we would then say that ozone has two conformations, and we draw them both, one on the left, one on the right. Because I don't know if you need to write this down, but it's critical. Please understand that this does not isolate or oscillate. It's not switching back and forth. This is not equilibrium. It is an average. And we know that for no other reason than because the bond lengths are equal. It's not like it goes long, short, short, long, short, short, long. These are not vibrating. They're not switching between a single and a double bond. It is a partial bond in both directions. Yeah?
So if there was like another oxygen on top.
Guess what we're doing next? Yeah. Yep. That's what we're doing next. I tell you what, some would mistake that for learning. Okay, so guys, let me then give you the go, no-go list. How do we talk about this, and how do we not talk about this? You already know, never let the words 1.5 or 1.5 bond cross your pen or your lips. So guys, how then do we talk about these things? So these are what are called resonance-stabilized molecules. Molecules that do this are called resonance-stabilized molecules. So guys, these resonance-stabilized molecules exist or we represent them as multiple conformations. There's another name, though, that you may hear in college or you can use in this class for conformations. They call them resonance structures. So you could put like an equal sign between those. Those are interchangeable. So ozone has 2 resonance structures, or ozone has 2 conformations. Either way is fine. And then, guys, we already wrote this down. These resonance structures, these resonance stabilized molecules contain what we call delocalized pi bonding. That's going to make a lot more sense when we get into chapter 9 and we start talking about hybridization. But for now, just understand it's what's called delocalized pi bonding. Yeah.
So are resonance structures a confirmation of a conformation?
No, they're just interchangeable. They're not hierarchical. So resonance stabilized molecules have multiple conformations, or resonance stabilized molecules have multiple resonance structures. Yeah. Okay. So guys, what words do you not use? First of all, 1.5 bond. But then, guys, some of you are going to get really creative on the test and you're going to call these resonance bonds. Oh no. Not a thing. But guys, to drive the idea home, let's do one more. And this, Kaylee, is kind of going where you were headed. Kind of. But it is going to get to your question. You guys good? You all caught up? Okay. So, guys, let's do this. I'm just going to go clean screen, and let's draw the Lewis dot structure for nitrate. So guys, please allow me to drive the process. We've got nitrogen, we've got oxygen, we've got oxygen. I already know that this is going to be trigonal planar, so we may as well draw it that way. Then we've got 5, 18, and 1. So again, public schools, 24. And then we've got 6 on the board. Check me. 18. Oh, shoot. 18. We good? Okay. So, guys, what we're going to do is we're going to put 6 valence electrons on each of the oxygens. You could put 2 electrons on the nitrogen. You would get to the same place. But this path makes it a little more obvious. So oxygens, full octets. Nitrogen, not so much. So now we need to form a double bond between the oxygen, one of the oxygens and the nitrogen. But guys, you see where this is headed. Which oxygen? Any of them, doesn't matter. So, guys, what we would actually then need to do, because we now realize that we're in this position where we have multiple resonance structures or multiple conformations, what we actually end up doing, and let me show you a way to make these faster, you've got to draw all 3 with a double bond in each of the 3 locations. So guys, here's how you do it. You're going to go nitrogen, oxygen, 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 then a double-headed arrow, nitrogen, oxygen, 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 then a double-headed arrow. Oh shoot, I didn't use my space very effectively. I'm going to actually start over. That's a mess. Oxygen, nitrogen, oxygen, 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 nitrogen, oxygen, 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 nitrogen, oxygen, oxygen. And then, guys, double-headed arrows in between. So now, guys, the thing that makes these structures a pain in the butt is having to draw all the dots for the electrons. So let me show you how to do this easier. We're going to put a double bond here, we're going to put a double bond here, we're going to put a double bond there. Now we need to draw in all of our unbonded electrons. And guys, drawing the dots drives me nuts, but you can do this. No, that's too many. Sorry. That's our double bonded guy. You can let lines represent unbonded electrons as well. Those are our 3 conformations. Those are our 3 resonance structures. Yeah? No, they're interchangeable. Yeah, I didn't teach that to you last year because it was important to understand bonded and unbonded pairs of electrons, but this is fair game. That's good. Yeah. Heck yeah, absolutely. Yeah. You guys good on the idea? Okay. So now, guys, let's get to Spencer's question. What does this actually look like? Because, guys, we know that it's not this. We know that this isn't alternating. We know that the actual structure of nitrate, oh, and by the way, you don't need to worry about it, but technically these should all be in brackets with -1, right? Because they're all nitrate. Guys, what does this actually look like? Well, guys, the answer is on 310. So go with me to page 310. Do y'all see it? So guys, in the middle of page 310, this is exactly what we did on the board, right? But what does it really look like? Go with me to 356. And look in the margin with the pretty pink thing. Guys, this is what this molecule actually looks like. So let me explain to you what you're looking at. Guys, the top image, and let me try to draw this the way they've drawn it. The top image is actually this. This is what nitrate would look like if it was just a localized pi bond. So guys, now we'll sort of talk about this now. So when a double bond forms, one of the 2 bonds, let me draw this. So this double bond right here actually looks like this. One of the bonds forms in the bond axis. You're going to find out in a couple days this is called a sigma bond. Then, guys, the double bond actually exists below and above the bond axis. So these 2 lobes together represent the second bond in a double bond, and that is what is called a pi bond. So here we have one bond, here we have the second bond, and those lobes above and below form the second bond of the pi bond. So guys, this is not a triple bond, this is a double bond. There's one bond here, and then the other bond is above and below. But that's not what's going on in nitrate. Guys, in nitrate, the bottom picture, that second bond of the double bond exists in all 3 directions simultaneously. That's what that pink blob is, going in all 3 directions above and below the plane. So what you would actually see is you would see a partial double bond here, a partial double bond here, and a partial double bond there in all 3 directions. So Spencer, you asked the question, what are the electrons doing? So this represents 2 electrons, right? So we've got a full shared pair of electrons there, call it a sigma bond, full shared pair there, sigma bond, full shared pair here, sigma bond, and then we've got partial sharing of another pair of electrons in all 3 directions simultaneously, and that forms the delocalized pi bond that goes in all 3 directions. That's the thing that's crazy. And you won't get into this until your sophomore year in college. But guys, Spencer, really insightful observation. Are these probability clouds? And the answer is yeah. You'll learn about this in organic your sophomore year. But in the same way that you understand at a pretty deep level atomic molecular theory or atomic orbital theory, when atoms bond together to form covalent bonds, they actually surrender their atomic orbitals, and they create a brand new type of orbital structure that are called molecular orbitals. And so, in the same way that we think about atoms as having orbitals, molecules also have orbitals that don't look anything like their atomic orbitals, and that's what that pink lobe is actually a molecular orbital that we call a pi molecular orbital. And then it gets even worse, because then you find out there are things called anti-bonding molecular orbitals, and I'll let your organic professor teach you about it. It's crazy. Yeah. Sigma star pi bonding, it's a mess. So anyway, all right, so guys, you feel uncomfortable with resonance? Go ahead, Kaylee. No. So this isn't a probability in the sense that when we study it, it collapses to a point. This is literally where those electrons are, and we know that because it physically changes the molecule, and we know that by bond lengths. That these bonds are shorter than single bonds, meaning there is some overlap there with that additional electron. Go ahead.
The second picture is like when you said some people draw it with like a dotted line.
Exactly. Right. Yeah. Yep. You got it. And it gets even cooler. Like, I don't know if you remember this. Hey, look, turn the page. 358. Molecular orbitals. Yeah, keep turning the page and you'll see all these sigma star bonding orbitals. And it's, never mind, we don't have to do that. Go back. Here it is. Go to the bottom of 355. Because I don't know if you remember in general chemistry when you drew this molecule. You guys, actually, we did this in lab. And there was a hydrogen coming off of each one of these. You actually built it with a model kit. And it looks like this. Do you remember this at all? And then you found out that there were double bonds alternating around the molecule. That's actually not true. This is actually also a resonance stabilized molecule, and the picture of it is at the bottom of 355. That double bond actually exists simultaneously, partially in all 6 directions, and that delocalized pi bond goes all the way around the ring. So it's interesting. You'll learn this in organic chemistry. The way that we draw this in organic chemistry is like this. You draw a circle in the middle to represent that it's got delocalized pi bonding. So, and hey, this is interesting. We'll do this in a couple days. Guys, look on page 354. We're going to talk about double and triple bonding. And actually on 354, at the bottom, that's what a double bond looks like. You do all, of course, see the similarities between that and my drawing. Right? So, but I mean, really, so you've got the sigma bond in the middle and then the pi bond above and below. But what does a triple bond then look like? And the answer is the left hand margin. So you've got one above and below that's going this way, and then another above and below that's going this way, 90 degrees out of phase with each other. And that's what a triple bond looks like. So, guys, wow, that was fun, but it took a lot longer than I thought it would. Other things we need to talk about? You're okay? Okay, so guys, the homework assignment is very short, but we already did that. Oh, by the way, guys, we're going to skip this for, guys, we already sort of got a flavor for this. We are going to talk next time about molecules that disobey the octet rule. We'll talk next time. Here's your homework. It is that short, but we also need to KWL Chapter 9. Guys, we're done with Chapter 8. We're moving now into Chapter 9, so let's do that for Tuesday as well. Man, that took a lot longer than I thought it would, but it's interesting stuff. So, we'll take a break.